during this talk. Our presenter will be Professor Tracy Webb. Should I maybe? Okay. So, hi everyone. Welcome to the first public talk of this new academic year. Today we have Professor Tracy Webb here with us, who is an associate professor at McGill. The name of the talk is From Clouds to Cosmic Giants, the Formation and Evolution of Galaxies. And this talk will explore the fascinating journey of galaxies from the birth of galaxy in the aftermath of the Big Bang to the complex system they have become. And Professor Webb will review current research and cutting-edge observational techniques from ground-based surveys to space telescopes, providing insights into how we measure and study galaxies. She will also touch on open questions and in galaxy evolution and future prospects in the fields, highlighting upcoming missions that will surely revolutionize the knowledge we have about these very fascinating galaxies, clusters, items. Thanks a lot. Before we start, however, I would like to remind you that the Space Institute, the Trottier Space Institute, and the Department of Physics is committed to equity, diversity, and inclusion. So we feel that we can only share our passion for physics and astronomy if everyone feels welcome and safe. So if in any moment of this talk you're feeling uncomfortable or you would like to reach out to us, please do so. We have some amazing volunteers who are wearing blue t-shirts tonight who will be very happy to assist you. We have a code of conduct that everyone can read. So yeah, you can find more about our activities on TSI Outreach at physics.mcgill.ca. And yeah, it's now a pleasure for me to introduce to you Professor Tracy Webb.
Thanks, Valentina. Can everyone hear me okay? I don't want to have to stand totally talking into the microphone, but I'll try and stay close to it. It's a real pleasure to be here tonight, to talk to you about a topic that I've been working on for a long time now, and that's the formation and evolution of galaxies. It's an area that I conduct research in. I'm not going to be talking about my own research tonight, but I am going to be talking about just the field of the evolution of galaxies and try and highlight some of the really interesting things about the evolution, the formation and evolution of galaxies, like Valentina said. So I'm just starting out with a compilation of what I think everyone in the room will recognize as galaxies of different shapes and sizes seen at different distances from us. And I want to start really though by talking about one particular galaxy, and that is our home, the Milky Way galaxy, which I hope everyone has had a chance to see at some point in their lives. This is a beautiful image of the skyline showing the Milky Way, or the parts of the Milky Way that we can actually see from here on Earth. It's actually a very large galaxy. There's more to it than you can see in this picture, but it's our home. It's our island universe, if you will, in this grand universe in which we find ourselves. But it is, of course, only one of about 100 billion galaxies within what we call the observable universe. And I can talk about what the observable universe is later on if anyone has any questions, but basically it's everything we can see. Might not be the whole universe, but it's everything that we can see. And we can count the galaxies or make an estimate of the galaxies that are in that volume of the universe, and it's about 100 billion. So our own galaxy, the Milky Way, is not really very special. Like our own sun, it's sort of a regular galaxy in a regular group of galaxies. Nothing really special, as you'll see, except that it is home to us. So I want to talk about how something like the Milky Way formed and how it evolves. And just to give you an outline of the topics I want to cover, and Valentina has already talked a lot about that, I just wanted to present a very brief outline. The first thing I'm going to talk about is how we think galaxies were sort of seeded after the very beginning of the universe, the Big Bang. Then we'll talk about how galaxies change over cosmic time. So the first part is really what we call the formation of galaxies. And the second part is more what we call the evolution of galaxies. And then and throughout the talk, I'm going to touch on how astronomers actually observe and study galaxies and how we can tell how they formed and evolved. Because it's obviously something, if you think about it, it's obviously something that happened in the past. And so how do we actually learn the way galaxies formed and evolved? So let me just start by getting everybody on the same page. Let's talk about what a galaxy is. I've shown you a picture of a galaxy and then hundreds of billions of galaxies. But let's zoom in on our own Milky Way and talk about the details of the galaxies that we need to be able to understand and explain when talking about the evolution of galaxies. So this is just a little schematic that I whipped up just to show you the kinds of components or the different components within a galaxy. And I'll try and point to different ones if the laser pointer works. The most important part, which may surprise you to hear, of a galaxy is this large black oval here that I'm showing you, which we call the dark matter halo. This is where, as you'll see, most of the mass of the galaxy resides, but it's in something that we call dark matter, which is a kind of matter that we can't see. And that's a whole talk in and of itself, which is actually coming up, I think, on the next public talk. So if you want to learn more about dark matter, you should come to the next public talk. But galaxies are, to first order, these huge dark matter halos. And then way down in the middle of this dark matter halo is the galaxy that you're used to seeing, like the Milky Way or in that deep image of space that I showed you. And it consists of this disk, which is blue, and I've colored it blue because it usually is made up of young stars, which are blue. And then there's the bulge, which is the central region, which I've colored as yellow because it generally is older stars, which are red. In this bulge and disk, we have stars, like I just said, and also the interstellar medium. And the interstellar medium is made up of all the gas and dust, all the stuff that isn't dark matter and isn't stars, basically. So a lot of hydrogen, a lot of helium, things like carbon and nitrogen, everything that you can imagine, all the stuff that we're made out of. And so it all resides in this bulge and disk component. And then there are also these globular clusters which sort of live within the halo. And we're not going to really talk about those at all tonight, but just I want to point out that there is stars, there is stellar mass, which lives up in this halo as well. But we're mostly going to be concentrating on the bulge and the disk here. Now, we live about 2/3 of the way out. So I've just placed a little arrow where we can be found in the Milky Way. Again, we're not in a very important part of the Milky Way galaxy. Perhaps the most important part of the Milky Way galaxy is this final component here, which is the supermassive black hole, which lives at the center of our galaxy. And some of you may have seen the press release of this image of the supermassive black hole at the center of our galaxy that was taken with the Event Horizon Telescope not too long ago. So we have a supermassive black hole, and I'll come back to that later. We'll talk more about that. We have stars like our own sun. We have globular clusters, which are made up of millions of stars. And some of you who are amateur astronomers probably like to look at these objects because they're very easy and fun to find in the night sky. And then finally, we have the gas and the dust, the material that's not bound up in stars that we call the interstellar medium. And so that's really a galaxy in a snapshot. Just to give you some numbers, galaxies are really big things. So a galaxy has a total mass of something like 1 to 2 trillion times the mass of our own sun. And that mass, as I talked about, is made up of dark matter, which makes up about 90% of the galaxy. And then we have gas and dust making up the next component, around 7%. And then stars, which is the stuff that we're used to seeing in the night sky, really only makes up about 3% of something like the Milky Way. The size that we're talking about is about 100,000 light years across the visible disk of the galaxy. So a light year, as we'll talk about in more detail later, is the distance that light can travel in a year. And so 1,000 light years, it basically takes light 1,000 years, 100,000 years, I'm sorry, to get from one side of the disk to the other. So they're really large and really massive. And they're not made up of the stuff that you and I are made up of. They are mostly dark matter. And just as an aside to that, I just want to remind everyone of this, what we like to call in astronomy, the pie chart of ignorance, because it's showing you what the universe is made up of. And again, this is a whole talk on its own. Most of the universe, the mass energy density of the universe is something called dark energy. And then the rest of it is mass. And most of that mass is dark matter, like we saw with the galaxy. And then we have gas and dust and stars and things like neutrinos and heavy elements making up a much, much smaller component. So the galaxy, in many ways, reflects the matter makeup of the universe. And it's really made up of stuff that is unlike the matter that we see around us today. But for the rest of the talk, I'm really going to be talking about that small component of a galaxy, which is the visible matter that you and I are made up of. So as I've already touched on, galaxies come in a wide range of shapes and sizes. This isn't an exhaustive compilation, but this is just a bunch of pictures of spiral galaxies taken by the Hubble Space Telescope, just to give you a feeling for the different kinds of galaxies that are out there. These are all actually fairly similar galaxies in that many of them are these spiral-like galaxies that I'll talk about more in a minute. You can see these spiral arms emanating outwards from the central region, and we're seeing this galaxy sort of face on rather than edge on like a disk that I showed you in the schematic before. So some of these galaxies you can see a little bit better are disky, and it's all just the orientation that we're seeing them in the sky. But galaxies come in an array of shapes and sizes. And for a long time, we've had a very simple way of describing the different morphologies of galaxies, or the sort of taxonomy of galaxies. And this was something that was invented by Edwin Hubble of the Hubble Space Telescope, who was an astronomer a long time ago. And he developed what we now call the Hubble tuning fork, which is just a really simple way of classifying galaxies. And all I want you to really take away from this is that galaxies do come in a range of shapes and sizes. We have these elliptical galaxies, which are shaped very much like a football. And they are huge. You can't really tell this in this image, but they are the most massive galaxies in the universe, much more massive than our own Milky Way. They're shaped like a football, or they're elliptical, hence the name. And they don't have a lot of gas and dust inside them. They're mostly stars and dark matter. Then we have two types of spiral galaxies. And these are the ones that I just showed you in the previous picture. And this is what our own Milky Way is. It's a spiral galaxy. It's shaped like a disc. When you see it face on, it has these spiral arms that emanate outwards. And spiral galaxies are differentiated by whether or not they have what we call a bar in the center. And you can see that bar here. It's just this straight object in the center, made up of stars and gas and dust. These galaxies are unbarred. They don't have that, and these galaxies do. I'm not going to talk any more about bars, but they are something that we need to explain when talking about galaxy evolution. This is the Hubble tuning fork. As I said, there's a whole bunch of galaxies that don't fit into the Hubble tuning fork, and these, in typical astronomy fashion, we just call irregular galaxies. And so anything that doesn't fit into the Hubble tuning fork gets called an irregular galaxy. And these are anything from these sort of amorphous blobs to things that look like they might be undergoing a collision. So this is probably a spiral galaxy that had another galaxy come straight through the center and disrupted the entire galaxy. And so these don't fit into that nice tuning fork, so we just call them irregular. Okay, so that's what a galaxy is. Spirals, ellipticals made up of dark matter, lots of luminous matter in the very center, stars, gas, and dust. How did they form? We see them around us today. They're formed in the night sky. They're evolving very slowly. Their formation must have happened a long time ago, shortly after the Big Bang, we think. Because the farther back in space we look, and I'll talk more about this in a second, the more and more galaxies we see. So they're there throughout cosmic time. And so we think they formed just after the Big Bang. And this is a diagram that I often like to show. It's very complicated, but I'll go through it kind of slowly, which is just an illustration of the idea of the expanding universe. So the idea is that we are here at the beginning, and there's something that we call the Big Bang. And this is the beginning of the universe, the beginning of time, the beginning of matter and energy. The universe gets larger as a function of time since the Big Bang. Right after the Big Bang, the universe is sort of, we call it a primordial soup. It's made up of all sorts of subatomic particles that are just flying around. There's not very much structure. But with time, structure begins to emerge from this primordial soup. And we don't really know why or how. We think it's something that we like to call quantum fluctuations, which is really just the popping in and out of existence of overdensities in the early universe that then grow by gravity. And that gravity pulls material in and starts to form more dense objects that then we think form into galaxies that we see around us today. So there's this long period of time after the Big Bang and after this early primordial soup of subatomic particles where structure is just growing slowly into the stuff that we see around us today. So that might be hard to picture. So I downloaded a little movie, which is a simulation from the Center for Cosmological Physics, which shows you how this structure can grow from a very smooth universe to one which has a lot of structure within it. And basically what's happening is that gravity is working to enhance areas of excess mass. There's more mass there, so it has a higher gravitational field, so it starts to pull in material, and dense areas get denser and voids get more empty. So hopefully this will work. There we go. And this is obviously very sped up, but you can see that we started from a very uniform universe, and areas like this, for example, had maybe just a few atoms that were more than areas like this, but it was enough to set off sort of a chain reaction of gravity and make these structures grow. So now we're going to talk about what's happening inside these structures. So these are basically giant clouds of hydrogen and helium, all the stuff that was made in the Big Bang. And they're collapsing under their own weight of gravity. And for a long time, we thought we understood this process fairly well. There was this sort of old textbook view of galaxy formation and evolution, which said that there were these big clouds at the beginning of the universe that had grown because of these quantum fluctuations, and they are collapsing under their own weight and eventually will become dense enough to form stars, and stars turn on and create a galaxy. The difference between the left column and the right column is sort of what we call a top-up versus bottom-up formation scenario, where maybe we start on the left-hand side with one gas cloud that then fragments and forms a whole bunch of stars that make one galaxy, versus having many gas clouds that merge together to form an even larger galaxy. So it's really just a question of, do you start with smaller pieces that you merge together, or do you start with one big piece that you then fragment? We now know that this is not a really good picture of galaxy formation and evolution. The actual picture is much, much more complicated than I learned in my original classes back in graduate school. And I want to just take a minute to show you a beautiful image or a beautiful simulation of how galaxies actually form. And this is quite a long simulation. We might not go through the whole thing, but I'll just talk a little bit about it. It's coming from the illustrious next generation simulation. What you're seeing here is the formation of a single galaxy. All of this material you see here is the gas that's infalling and forming this galaxy. Down here in the lower left is actually the dark matter, which is driving the gravitational collapse of this gas. And then over here on this other side, we just have the stellar component. And honestly, I can't even remember what this is. But the important component is this gas here, which you can see is forming a very dense component in the center. And gas is inflowing here. And then every now and then, if you pay attention, you'll see another cloud of dense gas infalling. And we're just going to take a zoom around for a second. And then it will continue. So if you keep your eye on this other dense component of gas, which is in and of itself a little galaxy, it will merge onto this galaxy and create, a giant mess. So this is very different in detail than those very simple pictures that I learned in my galaxy evolution textbooks. So let's zoom in on some of these processes a little bit more. So what are the galaxy growth mechanisms that we saw in that simulation? Well, the first one, which I think everybody saw pretty clearly, is that galaxies grow by accreting gas. So we have these gas clouds that are collapsing under their own weight. And as they collapse, they're bringing in more and more material. So there are these filaments within the universe of this material that you saw in the first simulation that are sort of funneling themselves into these nodes within the cosmic web where these galaxies are. These are both artist conceptions. I should just point out, I'm mostly showing you real images except for the simulations and a couple of artist conceptions. So this is what it might look like if you looked at the gas infalling into a galaxy, and you can see that it looks not unlike that simulation that I just showed you. So galaxies grow, we think, by accreting more and more material, and that material falls onto a galaxy, becomes dense, and somehow is turned on to form stars. This is a whole talk on its own as well. The formation of stars is probably one of the poorest understood areas of astrophysics today. So in many of these simulations, what we do is we just say, as soon as the gas gets dense enough, we turn on stars, because the stars are not forming naturally within the simulation yet. There's another growth mechanism that we saw in that simulation, and that is that galaxies grow by merging with other galaxies. Now, these are real images of galaxies put together along a merging sequence. So these are different galaxies which are at different phases of a galaxy-galaxy merger. So we start with two galaxies which are separated by a large distance, and we bring them together, and they start to interact with each other, and you can see they're changing shape. And as they interact with each other, you get these streams of material coming out, and eventually they sort of coalesce to form a more massive galaxy. And so this is one way that we think that we can actually take a spiral galaxy or two spiral galaxies, smash them together, and form a very massive elliptical galaxy, because the spiral structure is essentially destroyed in the collision. Many of you may know that the Milky Way is actually on a collision course to a nearby galaxy. And that is our neighbor, the Andromeda Galaxy, that's about 2.5 million light years away. And although it's 2.5 million light years away, it's moving slow enough that the whole thing is gonna take billions of years. So it's not something that we have to worry about. But if you were to be around in a few billion years, this is, again, a computer-generated image of what the night sky might look like. So we have our own Milky Way here, which has been distorted, and then we have the incoming Andromeda Galaxy smashing into it. And then finally, something that you couldn't see in that simulation was the role of supermassive black holes. So I mentioned that there's a supermassive black hole at the center of our own galaxy. It turns out, as I'll show you in a second, there are supermassive black holes at the centers of every galaxy. This is a Hubble Space Telescope image of a very large galaxy nearby called M87. Again, if you're an amateur astronomer, you may have actually seen this object through your telescope. You can see that it has this weird jet of material, this plume that's coming out of one side of it. There's probably a second one on the other side. We just can't see it because all the stars are in the way. And we think that jet is being generated by a supermassive black hole in the center of this galaxy. We've taken an image of that supermassive black hole, or of the event horizon of the supermassive black hole, again with the Event Horizon Telescope, just like we have taken a picture of the one within our own galaxy. So we have two images of the event horizons of supermassive black holes, which I can talk more about later if you have any questions. And we know that there's really these supermassive black holes at the centers of these galaxies. What do we mean by a supermassive black hole? Well, we're talking something like 6 billion solar masses. So not as massive as a galaxy, which is trillions, but still pretty big. These are very different than the stellar mass black holes that you may have heard about as well in the press. Those have masses of maybe 10 solar masses or something like that. These are really, really supermassive black holes. And as I said, we think that there are supermassive black holes in the centers of all galaxies out there. Basically, every galaxy that we've been able to do a measurement on shows that there's a supermassive black hole at its center. And there's a correlation between the mass of the galaxy in stars and the mass of the supermassive black hole, such that, and this may not seem strange to you, such that very massive galaxies have very massive supermassive black holes. And that kind of makes sense, except that the scales of a black hole and the scale of a galaxy are so different that it's very puzzling to astronomers how one can correlate with the other one. How does the very small scale supermassive black hole at the center of the galaxy know what kind of large galaxy or small galaxy it's living in? So this is one of the fundamental questions in galaxy evolution, is how do we produce this relation here? So as I said, although these black holes are small compared to galaxies, there's something about them that is influencing the evolution of galaxies. And we think that supermassive black holes can regulate galaxy growth through things like outflows, feedback mechanisms, and these huge jets that they produce. And this, again, is an artist's impression of what a supermassive black hole might look like with the jet coming out. We have seen evidence of this in real images. So these are just two fairly local galaxies and galaxies. This is actually a galaxy cluster with a supermassive galaxy at its center. This is an X-ray image, and what you're seeing here are cavities in the hot gas that have been blown out by the supermassive black hole at the center of the galaxy. And this is Centaurus A, which has these huge jets of material emanating out from the top and the bottom. So you can see that these supermassive black holes are really large scale in their effects. So they're affecting space on scales even larger than the galaxy. And so we think that they do a lot to the galaxy themselves and are probably creating this correlation that you see here. And finally, when galaxies merge, their black holes merge too. And this is an area of really active research in astrophysics as well. This is just a computer-generated simulation of two galaxies with black holes in the center that are in the process of merging. And as many of you may have seen in the news, when black holes merge, they create what we call gravitational waves. And these gravitational waves have been detected using gravitational wave detectors. And we can see black holes merge literally through the detection of these gravitational waves. Unfortunately, so far, we have not been able to reach the frequencies that we need to measure supermassive black hole mergers. So that's something in the future. So all the black holes that we've seen merge have been sort of 40 solar masses. We haven't seen these supermassive black holes merge yet, but we hope with future instruments like the interferometer called LISA, which you may have heard of, we'll be able to measure these supermassive black holes merging in distant galaxies. But we can still find evidence for them. So this is just, again, an artist's impression from a press release from the Atacama Large Millimeter Array, which is a radio telescope, which was able to detect two probable black holes at the center of this one galaxy. So probably what has happened is that this galaxy is the result of a merger. You can't really see much of the merger left over anymore. But if you look in its very center, it has two black holes that are about 750 light years apart. So they're getting really close to merging. So this is a large distance, but not for a black hole. Okay, so those are really the mechanisms that are important to galaxy evolution. So now let's talk a little bit about how these play out during cosmic history. And I really want to just highlight this idea that galaxy evolution is a process. It's not an event. It doesn't happen once and once only. These galaxies are evolving as a function of time throughout the history of the universe. And they're still evolving today, albeit slowly, as I'll show you. And so basically, this is just another schematic showing you this idea of the Big Bang happening at early times, having a very uniform universe that is then collapsing. Well, the material in the universe is collapsing under its own weight, and we start to form galaxies that we see today. So we're going to be talking about this whole process along here now, which is the process of galaxy development or evolution. Now, I know this is a really busy slide, but I wanted to show you one scientific slide, and this is the most famous scientific plot in my area of research. So I'm going to go through it pretty slowly. You can ignore most of everything that's on this image. What I want you to follow is this dot dash line here, which is really the compilation of all of the measurements that you see on this plot. Every one of these measurements represents hundreds, sometimes thousands of galaxies that have been measured. What you're seeing is the cosmic star formation history of the universe. This is the star formation rate averaged over all galaxies in the universe as a function of time, with time in the past increasing in this direction. So this is early times and this is late times. So this is today, 0 is today, and very early times, like 13 billion years ago, is over here with the 8. Astronomers like to work in redshift, but we don't need to talk about redshift at all today. So it's star formation rate as a function of time. And what astronomers have found over the last, I'd say, 30 years of work is that in the universe, as we go back in time, the star formation rate increases, averaged over all galaxies. So galaxies back in time were much more actively changing and building their stellar mass than they are today. And then it falls off again to very early times. So if I flip that around, what that's saying is that after the Big Bang, galaxies started to form and they started to grow their stars fairly slowly. And then they peaked somewhere here in their star formation rates. And then something has been shutting them off as a function of time ever since that peak. And this is a plot that we really strive to understand in galaxy evolution. We want to know why it has the shape that it does. Why did the star formation rate, the global star formation rate, peak right here? Why did it fall off so fast today? These are all open questions in astrophysics. We've labeled these three different interesting epochs in history as cosmic dawn, when stars first start to turn on. This is about 1 billion years, up to 1 billion years after the Big Bang. Then there's cosmic noon, which is about 10 billion years in the past. And then today we call it cosmic dusk. And so I may flip to that terminology. So cosmic noon is really this time in the past when there was a lot of action happening in galaxy evolution. But how do we know all this? So I mentioned that these points on this plot were the measurements of hundreds and thousands of galaxies. And basically, what we do in astrophysics, as you know, is we take observations with telescopes. And this is how we learn about what the universe was doing in the past. And I'll talk more about that in a second. But I also just want to highlight the use of simulations, because I've shown you a couple of simulations. There's some really amazing work being done with teams of theoretical physicists who run simulations of galaxy evolution in these supercomputers. So really, there's two things that we do. We take observations with our powerful telescopes, and then we try and interpret them using these supercomputers. So I've talked a lot about this idea of looking into the past and seeing galaxy evolution happening. And I want to talk a little bit more about this because I think it's a really amazing thing that the universe has done for us, which is the fact that light travels at a finite speed means that we see back in time when we look at galaxies which are very far away. If that doesn't make sense, I'll just go through it. When we think about the sun, for example, the sun is about 8 light minutes from us in distance. That means it takes light 8 minutes to get from the sun to the earth. And when you look up at the sun, which you should never do, you are seeing the sun as it existed 8 minutes ago. Alpha Centauri, which is the closest star to us, is 4.3 light years away. That means the light took 4 years to get to us. And when you look at Alpha Centauri, you're seeing it as it existed 4 years ago. These are not very interesting distances, in my opinion. What is more interesting is when we start talking about galaxies. So for example, I mentioned the Andromeda galaxy about 2.5 million light years away. There, we're seeing back in time 2.5 million light years. This literally means if there are aliens in the Andromeda galaxy with large enough telescopes that they can look at us here on Earth, they would not see us sitting in this classroom right now. They would see human beings as they existed 2.5 million years ago. So they would see, Australopithecine on the savanna of Africa or something. You're really, the light from the light from us is traveling through the universe, and it will just be reaching Andromeda today, the light that left 2.5 million years ago. Even Andromeda is not a very exciting distance. When we start talking about these 100 billion galaxies in the universe, now we're starting to talk about galaxies that are billions of light years away. And so we're seeing them as they existed billions of years in the past. And so we can literally take images of galaxies as they're evolving. We're seeing back in time. Telescopes are acting as time machines. So I just want to really make the point that we can never see one galaxy evolve. That's one thing we can't do in astrophysics. What we do is we take different snapshots of galaxies at different cosmic epochs and try and piece together a narrative of galaxy evolution. And so this is just one narrative of the way a massive elliptical might grow as a function of time, where each of these little circles represents a different snapshot in the history of its life. And this is going back in time, so we're going to larger and larger distances all the way back to the Big Bang. This is not unlike if an alien were to come down to space, down to Earth, and take a look at people at different phases in their lifetime and have to put together a narrative of human biology just from these snapshots of people of different ages. So the tricky part in galaxy evolution, the nice thing is that we have this time stamp because we know how far away a galaxy is, so we know how long the light has been traveling. But we do have to match up galaxies sort of with each other throughout history in order to construct this narrative. And of course, we take observations at different wavelengths of light, check the time, to understand different physical components and different physical processes that are happening. So for example, we might take an image of a galaxy at radio wavelengths, which looks very different than that galaxy does at X-ray wavelengths. So we try and work across the whole range of the electromagnetic spectrum. And here are some of the instruments that we use to do that. So these are some of my favorite instruments, some of the most amazing facilities that we have access to today. There's, of course, the Hubble Space Telescope, which has been active since 1984 and is still going strong. It's done some amazing work. It's responsible largely for that scientific plot that I showed you, that 30 years of research that people have been putting together. But it's now being eclipsed, of course, by the James Webb Space Telescope, which was just launched recently. And I'll show you some exciting results from the James Webb in a second. But I also just wanted to highlight the Atacama Millimeter Array, which is something that I mentioned earlier. This is a radio array down in the Atacama Desert Plateau in Chile, which is also an amazing ground-based facility. And it's observing at radio wavelengths, so sampling some very different components of galaxies than, say, the James Webb Space Telescope would. So these facilities really work in concert with each other. So I mentioned I was going to talk a little bit about some of the results from the James Webb Space Telescope. I just wanted to highlight this one. This is just a headline from the CBC not too long ago. These JWST deep fields, so by a deep field, I mean we pick a very empty part of the night sky and we image with something like JWST down for hours and hours and hours, take the deepest picture we can. And when we do that, we get something that looks like this. And you see thousands and millions of galaxies in a very small area of the sky. These deep fields are the deepest images of the universe that we have to date with JWST. And they're seeing furthest back in time, all the way to a few million years after the Big Bang. And what they're seeing is really amazing. One of the things that they found are these things that people call little red dots. And that's what you see here. And you can see why we call them little red dots. They're tiny little, very compact red galaxies. But they are shattering our understanding of galaxy evolution and really that whole narrative that I've just told you about, because they're very massive galaxies. They're also what we call quenched, so they're not forming stars at very high rates. And they have very large supermassive black holes inside them. And the question that astronomers are now trying to ask today are, how did these galaxies build up so fast, both their black holes, their stellar mass, and why did they shut off so quickly their star formation? So they really don't fit into that nice picture of the star formation ramping up and then shutting off to early times, or to late times, excuse me. These are galaxies which have clearly undergone a huge amount of star formation already, and something has shut off that star formation. And these little red dots are everywhere. We're finding them all over the place with JWST. And like I said, they really are shattering our understanding of galaxy evolution. So it's just amazing. Every time we launch a new facility or a new telescope, we find something new and exciting that we never thought would be there. We never thought these old galaxies would exist at 100 million years after the Big Bang. And yet here they are. The universe has been able to make them. So as I said, we also use simulations and supercomputers to help interpret what we see with observations. This is just a particular snapshot of something known as the Eagle simulation. And what these simulations are showing us is that energetic feedback from massive stars and massive, supermassive black holes is extremely important in shaping galaxies in ways that we don't yet fully understand. And that probably has something to do with the formation of these little red dots that you see here, because they have very supermassive black holes in them. And the leading theory is that those supermassive black holes have shut off the star formation. So somehow that feedback from that supermassive black hole has shut off the star formation. Still doesn't tell us why there's such a supermassive black hole formed so early. And I just want to finish the talk by highlighting this idea that we really make progress in astrophysics and galaxy evolution in particular by technology development. So one of the great things about astronomy is it has really led the field in technology development, especially image creation and processing. You may appreciate that in a telescope, we have a mirror, which is our light collecting bucket. And this is just a compilation that I found very recent of a bunch of different mirrors going from the Great Paris I can't even see this. The Great Paris Exhibition, telescope, which was a very small telescope in the 1900s, all the way up to the planned telescopes of today, such as the extremely large telescope planned by Europe, the giant Magellan telescope, which is going to be down in Chile. Here we have the James Webb, which is actually quite a small telescope. It's very powerful because it's up above the atmosphere. And here's the Hubble Space Telescope. So for comparison, this is a tennis court and a basketball court at the same scale. So we're really pushing the limits of these mirrors that we can make. And the bigger the mirror, the more light you can collect, and the higher, the more clear the image that you can create with that mirror. So this is really the frontier over here, these multi-segmented mirrors, which are 30 meters in diameter. And I just wanted to finish also with mentioning the Nancy Grace Roman telescope, which is like another Hubble that we're going to be launching in hopefully 2027. And the reason it's so exciting is that this is the Roman telescope here in Conception. And the Roman field of view, which is the amount of the sky that we can see in one shot, is shown right here. And this may not mean much to you. It looks like it's just full of galaxies, but this is the Hubble Space Telescope field of view. So the power of Roman is that it has this huge field of view, and it's going to be able to just survey huge amounts of the sky. And so what was really just like what we call a pencil beam survey in the past now can encompass huge areas of the sky, and we can start to really survey galaxies, billions and billions of them, start to do statistics with them, and really understand sort of the trends within galaxy evolution. I also wanted to take a minute to mention the Square Kilometer Array, because this is a facility that Canada has recently joined. So down here, you see the countries highlighted that have joined the Square Kilometer Array, and there's Canada. The Square Kilometer Array is a different kind of telescope. It's kind of like the Atacama Large Millimeter Array. It's a collection of many, many telescopes which are linked together electronically to create one large telescope that has collecting area of about a square kilometer, hence the name. This is just, again, an artist's rendition of what it would look like in the desert of, I believe this is Australia. There's going to be one array in Australia and one in Africa. And it's observing at radio wavelengths. So again, probing the universe at very different wavelengths, but still telling us some amazing things about galaxy evolution. Okay, so I'm just going to finish off then by summarizing everything that I've talked about and just really highlighting 4 takeaways. So the first thing I want to just say is that in studying the formation and evolution of galaxies, why is this important? Well, we're basically studying how our own house was built, right? We're studying the formation of the Milky Way, which is our island universe. It's home to all of the stars and the exoplanets and all of the life that might be out there in the universe. But also galaxies are the fundamental building blocks of the universe. And so if we want to understand how the universe evolves, we really do need to understand galaxies. We can learn about galaxy growth by simply looking back in cosmic time, by looking at galaxies which are further and further away, and therefore seen at larger and larger, or at earlier and earlier times. And then that scientific plot that I showed you shows us that we live in a very quiet time today. But in the past, the universe was really replete with star formation. Galaxies were really building up a lot of their stellar mass about 10 billion years ago, and then for some reason shut it all off for reasons that we don't fully understand. But we hope to understand that in the future. There's some amazing facilities which are coming online that have as their key science goals galaxy evolution. So I hope, especially for the younger people in the audience, that you'll pay attention to the press releases and learn about what's happening in galaxy evolution as these facilities come online. So I'm just going to finish by leaving you with this beautiful picture of the Andromeda Galaxy, the one that we're on the collision course with. This is a compilation of a ground-based image, which is shown over here, and a zoom in with the Hubble Space Telescope. The reason we only have part of it is because the Hubble Space Telescope has such a small field of view. And it was a real momentous effort just to get this much of the Andromeda Galaxy. But hopefully with Roman, we'll be able to tile this whole thing and really zoom in on how the Andromeda Galaxy lives and evolves. So I'll stop there and take any questions that you guys might have. I hope you've got lots. Thank you.
So another thing, if you don't want to speak up and just write down your question, you can just, I will come with a piece of paper and you can write down your question. But,
yeah. So I think there was a question over here. Yeah.
I have a question regarding dark matter.
Mm-hmm.
When 2 galaxies are merging, does dark matter interact?
Does it interact?
The other galaxies?
It interacts gravitationally, and it's really driving the whole interaction. But it doesn't collide with it's not, and the same thing is happening with stars. Most of a galaxy is empty space. And when 2 galaxies collide, the stars will pass right through each other. They won't collide at all. What you're really seeing in the galaxy collision is the gravitational interaction between the galaxies, and the gravity is ripping apart the 2 galaxies as they pass through each other. And so the dark matter is really doing the same kind of thing. So it's not interacting per se, but it is pulling on the dark matter from one galaxy is pulling on the dark matter from the other through gravity.
So it doesn't merge as regular matter would?
No, it will eventually form one large ball as all of the material is pulled into the sort of center of mass of the collision. But the individual particles of the dark matter will not collide. Does that make sense? Yeah. Okay. Yeah.
Like regarding the jets, like gas and stuff.
Mhm.
From like the event horizon, are they genuinely coming from inside a black hole?
Yeah.
We've thought, nothing can escape the black hole. Like,
Yeah, so this is true. So I'll just repeat your question in case people at the back couldn't hear. So the question is about the jets that emanate from a supermassive black hole. Where are they coming from? Are they coming from the black hole itself? Because nothing is supposed to escape a black hole. And you're right, nothing escapes the black hole event horizon. The jets we think are being, if I go back, see if I can go really fast. Sorry, here we go. The black hole is surrounded by material that's infalling. And we call this an accretion disk, simply because as the material falls in from all directions, physics tells us that it has to get flattened into a disk. And then that disk sort of spirals around and the material falls in and gets sucked into the black hole. That accretion disk is where the jet is coming from. So it's coming from outside of this event horizon and is being generated, we think, by magnetic fields in the accretion disk. But it's all very close together, relatively speaking. So when you look at something like this, you really can't tell. I mean, the jet just looks like it's coming from the very center. So it's very difficult to tell. But jet physics is another area of, I would say, a lot of open questions. We really don't we see these jets. We can see the effect of these jets on the hot gas within galaxy clusters, even these cavities, but we don't fully understand how they're formed. But they must be formed outside of the event horizon. I'm not sure who had their hand up next.
What's the first, black hole or galaxy?
No, we don't. No, that's the short answer. What came first, a black hole or a galaxy? Right after the Big Bang. And this is an area of active research. There are people at McGill who do this, theoretical physicists. So maybe someday they'll give a talk on it. But we really don't know. We originally thought with that sort of toy model of galaxy evolution that the stars and the galaxy would form first and then would grow a black hole in the center. But now with these little red dots, we're finding these galaxies with huge supermassive black holes already. And so the thought is, well, maybe the black hole forms first and then pulls in material around it. So we really have no idea. Yeah, it's a good question. Yeah. That's a really good question. How can we tell how far away a cosmic object is? That, again, is a talk in and of itself. Basically, let me see if I can, there's different ways of doing it. Some cosmic objects, which are very close to us, can be directly measured. So for example, we can take radar, which is when we fire radio waves at something and it bounces off of something and comes back. And we take the time it took to go there and come back again as to measure the distance because we know how fast light travels. We can do that for some of the planets, for example. But anything further than a planet, we have to get really tricky. And with galaxies, the way we do this is that we use the expansion of the universe. And the expansion of the universe tells us that galaxies which are farther away are moving faster. Okay, so that is just a consequence of the fact that everything exploded and the stuff that was moving faster is now further away. You can think of it like that. And so that means that if we can measure the speed at which a galaxy is moving, then we can guess how far away it is. And the faster a galaxy is moving, the farther away it is. And we can measure how fast they're moving through something called the Doppler shift. And this is the same, you know exactly what a Doppler shift is. A Doppler shift is the same thing that makes a siren change pitch as it goes by you. Or if you go to the Grand Prix, you hear the cars going around the track. They change their sound. They go like that, right? That's a Doppler shift. As they come towards you, they make one sound. And as they go away from you, they make another. And the faster they're moving, the more their pitch changes. And we can use that same Doppler shift with light and measure the shift in light, like the shift in the pitch of light. And that tells us how fast a galaxy is moving. And then that then tells us how far away it is. But there's a whole process. It's really complicated. And there are people in astronomy whose job it is only to measure distances. I'm not one of them. Yeah. Yes. Mm-hmm. That's another area of research because it's very difficult to measure the distribution of the dark matter, and the way, because we can't see it for that very reason. That's why we call it dark matter. It doesn't interact with light, so it's not glowing, it's not emitting light, it's not scattering light, it doesn't cause a shadow. There's no way to see it. So the only way we can tell it's there is through its gravitational pull. And so we have to map out the distribution of dark matter by looking at the motions of matter that we can see. And in doing that, we think the dark matter is fairly uniform. It's in a big circle or a big sphere around the galaxy, the visible part of the galaxy. It's probably a little more condensed in the center than further out, but it's very smooth. But it's very difficult to measure this because, as you saw in that image, the dark matter extends well beyond the visible matter, and you need visible matter as a tracer to see what the dark matter is doing. So we don't really know where the dark matter ends, that type of thing. It's very difficult. Yes?
Farther the object is and the smaller it is in space. It's not just part of my relativity. And I'm thinking that the same thing like and it does not work smaller.
Yeah, so I think you're talking about a couple things there, if I understand, and you can correct me if I've misunderstood your question. So the space has a shape to it. Is that what you're talking about? And the fact that in the past, the universe was smaller? Yeah. So the galaxies were actually probably bigger compared to the universe in the past than they are today, because they have sort of a fixed size. They're big. They're 100,000 light years across. Even the small ones are still quite large. So they're actually bigger in the past compared to the overall universe.
Here's a planet. Here's the size of the planet. We can go far into.
Oh, yes, yes. Sorry. So that, yes. So we can do that with galaxies as well. And this is another way that we can measure distances, is we assume that the galaxy has a uniform size, say 100,000 light years, and we see how big it appears on the sky, and we can measure how far away it is. Yes, the problem with that is that not every galaxy is the same size. So it gets difficult to tell if you're looking at a small galaxy close by or a large galaxy far away. Yeah.
Wondering if there's any way if there's any data telling us that there's a certain trend that is going to follow, or that might just be a metastable point.
You mean the at cosmic noon? Yeah. Sorry, I don't fully understand your question. So forecast it. In theory, that's what the simulations should do. The simulations in the supercomputers start with a very smooth universe made up of hydrogen and helium and dark matter. And then you introduce density fluctuations and allow them to grow. And they should, from that point, from first principles, then predict everything that, in a general sense, that can happen in the universe. And they should predict that there was this peak at cosmic noon. But the simulations are very complicated and are also very tuned to the observations that we see. So it's a little bit tricky to pull out what's a true predictable from the simulation and what we've just fine-tuned ourselves to make happen because we know it had to happen. So other than the simulations, I can't think of anything that would tell us that that's the way the universe should behave. I mean, it sort of makes sense. As the universe expands, things are getting farther and farther away from each other. The gas is having a harder and harder time falling in. You use up gas. So the general idea of why it should shut off kind of makes sense from that point of view. But why it has the exact shape that it does, we don't know. Oh, do we have one online? Yep.
Question is, do you expect the galaxy evolution field to develop as well as the exoplanets field? Will it be strictly reserved for the theoretical side, or will observational astronomers have career?
Good question. Yeah, so it's okay. So there's a lot of questions in there. I would first say it's a very different field than exoplanets, because exoplanets, the study of exoplanets is really at its infancy, and galaxy evolution, we've been banging away at this for, well, since Hubble in 1929. Hubble was the first person who showed us that galaxies were actually these huge conglomerations of many, many stars. That was back in 1929 or late 1920s. And we've been working at it ever since. So that's 100 years. And so it's in a very different state than exoplanets. But I would say throughout all of that history, observers and theorists have really worked in tandem together and have always really shared the limelight. So I think that there's not going to be any shortage of jobs for observational astronomers like myself, I hope, since I'm training them. Yes.
Is it possible that
Yeah.
really big non-elements in what story you that is particularly
Formed from. Yeah. So, yeah.
so fast.
Yeah, that's a really interesting idea. And not one that I've heard before. So I'm thinking about it for the first time. And I think there's that. So what can I say? There's no evidence for it, but that doesn't mean it's not the way. We know very little about the early universe and the original fluctuations from which all the structure grew. So your guess is as good as mine at that stage. And I think, again, there are people working on this and trying to understand. So we have a professor here, Dr. Robert Brandenberger, who studies objects called cosmic strings, which are ways of, they're different than string theory, but they're ways of seeding. They're getting at what you're saying. It's a fast way of seeding an overdensity very quickly that can then grow and form these supermassive black holes and large galaxies really fast. So it might be something like that. Yeah.
Yeah. How realistic is it possible for human settlement on Mars in this future generations?
Oh gosh, that has nothing to do with galaxy evolution. So I really, again, yeah, it's space. But I'm not an expert in it, is what I mean. Yeah, I think that settling, well, I don't know about settling, but having first people on Mars is well within our grasp, and probably something that we'll see in the near future. Settling Mars is a different story, because of course that requires, terraforming in some way. But I think people will be there pretty soon. Lots of hands went up when I said that. Yes? Yeah.
Probably, I don't know, but when do galaxies come to an end? Like, do they implode? Do they burn off?
Yeah. So galaxies thus far don't die. They slowly fade. So if they live on their own, they slowly fade and get older and older and older, and the stars don't form, new stars don't form. And the galaxy will become redder and redder, and the central supermassive black hole will get starved. And so we can get these really ancient galaxies, even in the local universe. Well, even in the early universe, we see them, and we definitely see them in the local universe. But in the future, this is something that is going to be a growing concern for all galaxies. As the universe expands further and further, if that's what it does, then galaxies will continue to get further and further away from each other. And all of these galaxies will become ancient and old and sort of dried up. And yeah, but they don't implode. They have enough energy to keep themselves sort of afloat. But what really happens is the stars get really old and the black hole gets starved, and yeah.
So how do we understand the significance of these little red dots? Is it possible we can revisit that graph that you showed?
Sure.
We'd be able to,
I can find it.
oh, sorry.
Oh, here we go. Yep. Oh, the line one. Okay. Yeah. Good question. So these little red dots live way out here. So at redshift 7, 8, 9, 10, when the universe was less than 1 billion years old. You can see on this plot that sort of it all goes nuts in this regime. So we have really nice measurements out here with very small error bars. You can see the trend very nicely that they produce. And then out here, we've got these measurements that have these huge uncertainties on them. And so what this is really saying scientifically is that anything is possible out here. We really don't have it very well constrained. And so these little red dots, there's two things that matter. One thing is how fast they were forming stars in the past. And we think they must have been forming stars very rapidly, which would place them very high on this graph. But they are actually, I said that we find them everywhere, but they are relatively rare. And so when you add them up, when you take their average over the volume that you've searched, it brings them down a little bit. So they're galaxies which are forming a lot of stars, but might not necessarily be contributing to the average very well.
Yeah.
So it's unclear to me where they would fall on here. And that's what but this is exactly what people are trying to do, is count them up and figure out where to stick them on this plot. And yeah, and I mean, this plot doesn't even go far enough now for some of the red dots that they found. So, but it might pull this tail up, and it might tell us that, as some people have suggested, that this is a flatter curve than it would suggest here. And that star formation turns on very rapidly. And so it's almost like a step function, like there's nothing, 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 and then boom. And then it's flat for a long time. So that's a scenario that's possible. Yeah. Yeah, no problem. There's one way at the back. Mm-hmm. Does the nature of the light get changed by the gravitational field around it? Yes. Okay. I just wanted to make sure I heard. Yes. There's something known as a gravitational redshift. So redshift is this Doppler shift that I was mentioning before, where the color of the light changes because of the motion of the galaxy. And gravitational redshift is the change in the color of the light because the gravitational field is essentially stealing some of the light's energy. And so if light is trying to escape from a very dense object, like a black hole, but it's outside the event horizon, it can be shifted in its color because of that.
So is it possible that if we measure any galaxy far of it from here, that the light is getting affected by the gravitational?
Yeah, it's a small effect though compared to the velocity. So we think that the velocity is dominating, but it definitely is playing a role. But it really becomes more important for things like white dwarfs or neutron stars, these very dense objects where the light's coming from the surface. I think there is one more question. Yeah. Yeah, so the physics yeah, so again, a talk on its own. It's dominated by the gravitational pull of the dark matter. But what I was showing you in that first simulation was what the gas is doing. And the gas is able to interact with itself. And so there are some laws of physics that surround gas dynamics that play a role and that have to be input into these simulations. So these simulations now are often called magnetic hydrodynamical simulations, and they have magnetic fields, and they have the hydrodynamics of the gas as well as gravity. So there's a lot of physics that goes into it. Some of that physics is not well understood. And so it's kind of tuned a little bit to match what we see, and is not, as I said before, necessarily emerging kind of from first principles in the simulation. Whoops. So that's still a bit of a problem. Part of the problem with these simulations also is a resolution issue. If you want to simulate something really, really big, it's hard to simulate simultaneously what's happening on very small scales. And so some of the physics is dominated by what's happening on small scales, and you can't resolve that if you want to get I mean, you could, but it would take 100 years to run the simulation in your supercomputer. So you're limited there too in the physics. Oh, okay, last question.
Do problems that your show for galaxy formation require of inflationary epoch?
No. No, that's the short answer. So inflation, I really skipped over. It's this hypothetical time early in the universe when the universe expanded very, very rapidly. Sounds like you know about it. And it's really important for setting up those initial perturbations that galaxies grow from. But galaxy formation really takes over after inflation. So what is happening in inflation is sort of setting up what we call the initial conditions, but then galaxy evolution just runs from those initial conditions.
It doesn't work.
Well, inflation is a way of setting up those initial conditions. So there are alternatives to inflation that also set up the initial conditions. So those also work, but they are less favored by theoretical physicists.
What is keeping us from getting closer to the Big Bang? You mentioned like it's a couple of 100 years.
Oh, yeah. So, well, there, the limitation is that we are observing stars. And so at some point there are no stars yet. And so we have to start observing other stuff. And we don't have really the technology to observe that other stuff yet. We have, the oldest picture we have of the universe is 380,000 years after the Big Bang. And that's known as the cosmic microwave background, which you may have heard of. And it's sort of the afterglow of the Big Bang. And it's actually physically impossible to see beyond that because the universe is so dense that you can't see through it. So that's really the limitation, but that's way before these galaxies that we're seeing. So the galaxies are really, people are still searching for the next most distant galaxy. And so we haven't reached the limit yet, but at some point there are no galaxies yet to see.
There are no more questions. Would like to end this call by thanking.
Thank you. And I'm happy to hang out if anyone has any other questions that they want to ask.
Before, take the microphone. So at the beginning of the talk, we asked you to, if you wanted to fill out a form to understand the demographics of the audience of our talks. I would like now to announce the winner, because who filled out the form entered a raffle, and it's gonna be Lily Sakas. So when you go out, you can take the mug that is on the table. It's yours. Also, I wanted to introduce the next public talk, which is happening again here at McGill with the location to be determined. It's going to happen on October 30th. And it's going to be a dark matter panel. So we're going to have two speakers, Kathleen Schutz, a professor here at McGill, and Yashar Hebzadeh, who is a professor at the University of Montreal. And every speaker is going to give a talk, and then there's going to be a 30 minutes Q&A session. So I hear there were a lot of questions also regarding dark matter. So I'm sure this is going to be something of interest. Again, thank you so much. For someone who is not in astrophysics, it's always very fascinating to realize the magnitudes and the time scales at which like astrophysicists and astronomers work. It's really fascinating. Thanks. And thanks for joining.
So do I have to?
Yeah, so I think you just stop sharing, and yeah, I will end the